If you think back to all of the concepts we defined for the linear algebra of Euclidean vector spaces, you'll realize that almost all of them were defined just in terms of the vector operations addition and scalar multiplication. But for a general vector space, we have those two operations, so we can make all of the same definitions for general vector spaces as we did for Euclidean vector spaces. So here are some examples of the sorts of things we can do. We can define linear independence in any vector space. So, a linear independence, a collection of vectors is linearly independent if and only if the only linear dependence relationship, so only if this equation has only the trivial solution. Right? But this definition, we can make this exact same definition for general vector spaces because all we need to make this definition is vector addition and scalar multiplication. And also, I guess we need something. We need a zero vector. We need an additive identity. But general vector spaces have those three things, and so the definition of linear dependence is exactly the same for general vector spaces as it is for Euclidean vector spaces. And the same is also true for subspaces. Right? A subspace is some subset of vectors that contains 0. So 0 has to be in your subspace. And your subspace has to be closed under vector addition and also closed under scalar multiplication. But again, these three all make sense in terms of general vector spaces. So a subspace of a general vector space is just some subset of your general vector space that contains 0, is closed under addition, and is closed under scalar multiplication. You can see all of these definitions are going to carry over to general vector spaces in exactly the same way. Another example, bases. So a basis is a collection of vectors in your vector space that span the vector space and are linearly independent. But the idea of span makes sense in a general vector space, and the idea of linear independence also makes sense in a general vector space. So we can talk about the basis of a general vector space. And since our proof that if you look back at our proof that every basis has the same number of vectors in it, that will also work for general vector spaces, and so we can define the dimension of a vector space just to be the number of vectors in a basis. Right? All of this works exactly the same as for Euclidean vector spaces. The idea of a linear transformation and all of the surrounding ideas also work exactly the same way. So the definition of a linear transformation is just some function from one set to another, so that if you take some linear combination of two vectors in your domain space, you get the corresponding linear combination of image vectors. But once again, this definition only uses vector addition. This uses vector addition both in the domain space and in the range space, and uses scalar multiplication in the domain space and the range space. So, but since it's just using vector addition and scalar multiplication in those two vector spaces, this definition makes sense for general vector spaces, right? These V and W don't have to be subspaces of some Euclidean space. They can actually be a general vector space. The idea of being onto also makes perfect sense for general linear transformations, right? Being onto is just saying that the image of a linear transformation is the entire range space, but there's nothing special about Euclidean vector spaces in this definition. This definition makes sense for general linear transformations between general vector spaces. And the same for one-to-one. One-to-one essentially is saying that the kernel of your transformation has to be just the 0 vector, but since every domain vector space has a 0 vector, this definition makes perfect sense for general linear transformations. Same for isomorphisms, right? An isomorphism is a linear transformation from one vector space to another with a linear inverse. But all of these things make perfect sense in the context of general vector spaces. One thing that we have to be a little bit careful about is, we had this proof for Euclidean vector spaces that if you have a map from a Euclidean space to some subspace of another Euclidean space, and T is, the theorem was that if you have a map between two subspaces of Euclidean spaces, like this, M, and the dimension of V equals the dimension of W, then what we proved is that T being one-to-one is the same as T being onto, which is the same as T being an isomorphism. But this is actually only true if these vector spaces are finite dimensional. Now we didn't really notice this requirement before, because since we were talking about subspaces inside of Euclidean subspaces, they have to be finite dimensional. But this result is actually not true if your vector spaces aren't finite dimensional. Of course, almost all of the vector spaces that we are going to work with are finite dimensional, in which case this statement is still true. All right, so we can define the kernel, we can define the image. They are still subspaces, right? The arguments that we use to prove that the kernel and image of a linear transformation are subspaces works exactly the same for general vector spaces as it does for Euclidean vector spaces. And the ideas of the matrix of a transformation and coordinates relative to a basis also work exactly the same for general linear transformations as for subspaces of Euclidean vector spaces. Remember, the idea with the matrix of a transformation was if you have a linear transformation like this, and you have some basis for V, and you have some basis, I guess I'll call it S, for W, then we have this coordinate map to some Rn, and we have this coordinate map to some Rm. So I guess we have to have V and W, the dimension of V and W being finite for this to make sense. The matrix of a transformation is just the matrix that fills in the gap here when we invert this linear transformation. Well, this all makes perfect sense, right? To make this definition, we didn't have to use any special information about V and W or this linear transformation T, other than that V and W are vector spaces, general vector spaces, and T is a general linear transformation. So we can even define, using this trick, we can even define the matrix for a general linear transformation between two general vector spaces. In this case, we really do need the bases to make sense of having a matrix, because there's no ambient Euclidean space for V and W, right? V and W aren't necessarily subspaces of Euclidean spaces. They might be some other weird kind of vector space, like a vector space of matrices or a vector space of polynomials. So in that case, to get a matrix, you really do need to have a basis so that you can get coordinates relative to that basis. But with that little wrinkle of requiring a basis, the whole argument of how you can get a matrix for a linear transformation works exactly the same way.